Started today. Good morning, everyone. I hope you've been having a good morning. I am Aditya Amburia, a senior product manager at Verkada, where I lead efforts on the cameras product team.
My name is Alan Anderson. I've been at Verkada for about 5 years. I'm a director of engineering. I was born and raised in a little rural town named Colstrip, Montana. And when I was growing up, this was in the age of dial-up internet, where I would, if anyone remembers Napster or iMesh, it would take me, overnight I would be able to download a couple of legal MP3s. And
Few people remember.
Yeah, few people remember, you can tell. And basically, we've come a long way since then, and I'm really excited to be able to show you what we're able to stream across the internet, which is significantly better than those years back in the 90s.
Exactly what Alan said. Today, Alan and I are excited to talk about the work the team has been doing to make sure that we deliver the best-in-class video quality and a seamless streaming experience with Verkada cameras. So, streaming on command is not just one of the first experiences our customers have with Verkada cameras, but it's also the most common. Whether you're investigating an incident or ensuring operational procedures are followed within your premises, or even conducting live monitoring, the ability to stream high quality video quickly and reliably on command is crucial, which many of you experience on a daily life. It's something that we deeply committed to delivering. We see this time and time again by the way that our customers actually utilize the Verkada platform. Today, across 26,000 customers that Verkada has, we're streaming 400 years worth of footage every week on command. Let's just take a moment for that to sink in. 400 years every single week. And this is incredible to see the scale of usage and the trust that our customers place in our platform. When we see where does most of the streaming happen, it's been mostly distributed between command web and viewing station, with command web accounting for 40% and viewing station accounting for 60% of the streaming traffic. Now let's take a closer look at command web. Most of our users use Google Chrome, that's about 65% of the users, rest of them are 28% are on Microsoft Edge, while other users are distributed across Firefox and Safari. So at Verkada, focus has been to delivering convenience of accessing and monitoring cameras in real time, no matter where you are or which platform you choose. Now, for us to ensure that we're delivering the best experience possible, we have defined 3 key guiding principles for us: video quality, time to first frame, and latency. Let's talk about video quality. We all know what a bad or a good video looks like. So instead of me just talking about it, let me show you a side-by-side example where you can visibly see the difference. First, you'll see the image on the left, which is using H.264, while the one on the right uses H.265 codec. Now, you can see H.265 codec is way more efficient in compressing the video and providing better quality at even lower bitrate. Alan will dive a little bit deeper into this technology later in this session. Second, you see the image on the left is using static bitrate for our standard quality, while the one on the right is actually using variable bitrate for our high quality. So here, variable bitrate actually dynamically allocates more bits to a scene when it requires it. It ensures that we deliver the highest quality video while optimizing the bandwidth consumption. Now, the next up, our guiding principle is time to first frame, or what we call TTFF. So what is time to first frame? Well, time to first frame is the time it takes when you start a stream to when the first frame of the video actually loads on command. Now, you might be wondering, why does time to first frame matter? Well, it matters because spinners suck. Nobody likes sitting there waiting for a video to load. Right? I see a lot of nods in the audience right there. We all agree. And if you see, we have come a pretty long way. Back in 2017, when we first launched our cameras, you had to wait for 6 seconds for the first frame to load. which is a little too high, to be honest. And then fast forward that to 2024, we've reduced that down to mere 1 second. That's major improvements that you see. And we'll talk about it later in the session how we achieve this. A third guiding principle is latency. Latency is the time delay from the moment the video is captured to when it's available for the first time for you to stream. Think of it as the lag with the real world. Well, why does latency matter? There was a point in time when, sorry. So there was a point in time when the most cutting-edge technology actually looked something like this. Well, we're not in 1980s anymore. It's 2024. We have self-driving car and generative AI at our fingertips. Expectations have changed, and rightfully so. You can see that how this can create huge issues where if you're waiting, trying to aim a camera, and then you have to wait for 10 seconds for the feed to load on command, that's just not a good experience. And that is why latency really matters. You can categorize latency into 4 main buckets. Back in 2017, when we first launched our earliest cameras, we were at 10 to 12 seconds. And to be honest with you, that was embarrassingly a little too high. Fast forward that to 2024. We have reduced that latency down to 900 milliseconds, which is incredible. That has a huge impact for our customers. And we'll dive a little bit deeper into how we achieve this. Now, I'm going to hand it over to Alan to talk about how these principles have guided us to implement technologies that have significantly improved the customer experience.
All right, thank you, Aditya. I do also want to mention, as we dive into some of these technologies, I'm going to go deeper than some of you may understand, and I'm going to be shallow than some of you may understand. I want this to be somewhat interactive, so feel free to raise your hand and ask a question as we go. If we get too many questions, then we can defer some of them to the end. But I don't want to lose anyone, and if you have a question that occurs to you, I'd be happy to address it. So first, let's take a walk through some of the technologies that we have used over time. As I mentioned, I started at Verkada in 2019, and at the time, there was exactly 1 engineer that was focused on streaming, and plus me. And so we were building out the streaming technology with a pretty small team. And at that time, we decided to use the most tried and tested technologies available at the time. These were the most ubiquitous, they were older, they were well tested. So naturally, you can see up here, we started with H.264 as our video codec. And then we also used transport streams as the video container. In order to transport that video across the web, we used HTTP1 technologies as well as HTTP live streaming. And then on the browser side, we used an open source library called hls.js. Again, these were the right decisions for the time, but we wanted to advance and improve all of those metrics that Aditya just ran us through. So fast forward to 2021, our next generation of streaming technologies were released. We were still using H.264 as the codec, but we containerized the streams using fragmented MP4s, or MPEG-4. I'm sure a lot of you are familiar with MP4. It is a much more ubiquitous technology. It has more use cases. Transport streams are primarily used for live broadcast streams. So then we also switched to WebSockets and media source extensions. This gave us more control over the media from the browser side and allowed us to reduce the time to first frame and improve our streaming latency. To go to media source extensions from HTTP live streaming, for example, we went from roughly 12 to 14 seconds of latency down to 1 to 4 seconds of latency in the typical case. Fast forward to today. 1 year ago, we announced our transition to the H.265 video codec, and we continue to use fragmented MP4s as the container. And for our transport, we've advanced to HTTP2 with Web Codecs API. Now, the Web Codecs API was just released across all of the major browsers last year, and H.265 was released to Chrome in 2022. So the reason we're able to use these technologies today is because of the broad support across the browsers, but they are very new and advanced and innovative technologies. And naturally, they all provide us with better latency, better time to first frame, and better video quality. For the remainder of this presentation, we'll do a deeper dive into H.265, HTTP2, and web codecs. So first, about video quality. When we announced H.265 last Verkada 1, we were very excited because, as Aditya mentioned, you get 2 times better video quality for the same bitrate of H.264. It's a much more advanced compression technology. Now, that doesn't mean that it was free and easy to implement, so I'm going to dive into some of the challenges that we encountered as we were implementing it. First, sorry, the picture didn't load. First, I'm going to talk a little bit about how video works at a super high level. Again, this is probably too basic for a lot of you, or maybe it's the right level. So video, you can think of it as a series of static images that are played in rapid succession. Our videos record at 24 frames per second, so we're sampling the video every 24 seconds, every 24th of a second, or about 42 milliseconds, to create 1 frame. And then, each and every frame you can think of as a matrix of pixels. And each pixel is represented by 1 color. So if you imagine video, you need to encode enough data for each and every pixel on each and every frame. And that can be a lot of data. I think back to my times on dial-up internet. Video streaming at that time would have been completely impossible. And let's see why. So, in the 90s, the primary streaming resolution for videos was standard definition, or SD video. 460p is often referred to as. In order to stream 1 SD stream in uncompressed format, it would require about 160 megabits per second of video. My dial-up connection was 56 kilobits per second. So naturally, to be able to stream 1 uncompressed video stream takes a lot of data, and that's just SD. Fast forward to HD video, it requires over 400 megabits per second. And for full HD, 1080p, is about 1 gigabit per second of video. Now, keep in mind these numbers can change depending on frame rate, bit rate, and color bit depth. But for this example, we're using the same numbers for all of the technologies. So full HD requires about 1 gigabit per second of bandwidth. So 4K, you can see it's starting to grow exponentially, would require a 4 gigabit per second connection, and lastly 8K would require about 16 gigabit per second connection. Completely unmanageable. There's no way we'd be able to stream uncompressed video across the internet. So what is the solution? You might have deduced it by the fact it keeps saying uncompressed video. We need to compress it, and that's exactly what the codec does. So what is a codec? I mentioned H.264 and H.265 as 2 different video codecs. Codec is the combination of 2 words, codec, compressor, decompressor. Some people also say coder and encoder. Coder and decoder, sorry. So compressor, decompressor is codec. So how does this work? I'm going to talk over, in high level, the technologies that video compression relies on. Here we're going to talk about temporal compression, or over time. So the way that we represent video is by frames. So this is inter-frame compression. So you imagine here we've got 2 frames from a Verkada camera. They're 42 milliseconds apart, so very little has changed between the 2 frames. The only thing that has really changed is the truck in the top left. Wow, that's pretty blurry, isn't it? Sorry about that. So the truck in the top left has moved. So you can imagine if you want to compress this, there's a lot of data that's similar between these 2 frames. And we can represent that data in a much more efficient way. If you subtract these 2 frames from each other, you've got the 1 frame on the left, and then the second frame, the difference between the 2 frames shows that box on the right side. The only area that has moved is that truck. Everything else has stayed basically the same. So, how do we do this? We can transmit across the internet the first reference frame, and then you can transmit the difference between the two frames as your second frame. And this will only require about 675 kilobytes of data as opposed to 1 megabyte of data. That's over a 30% improvement across 2 frames. Now, if you imagine if you did this over and over across multiple frames, that compression becomes significantly more efficient as well. So I just briefly described how temporal compression works. Does anyone have any idea what the other type of compression is that video codecs use besides temporal? I do have a gift card for merchandise at the merch store. Ephemeral? No?
Spatial.
That's a good guess, I appreciate it. What was that?
Spatial.
Spatial, that is correct. I'll hand this out, we'll save it for you here. So spatial compression. So let's just briefly cover what spatial compression is. You can imagine that each pixel in a picture typically will share attributes with the pixels around it. So here you might see the white pixels for the crosswalk. You might see the red pixels for the bricks on the sidewalk. You can represent those pixels very efficiently by approximating it according to the pixels that are surrounding it. So this way you don't need to save every pixel of every single frame. You can compress it both spatially and temporally. So let's talk a little bit about, as Aditya already mentioned, the breakdown of our users and which browsers they use. And then I'll transfer into why that actually matters for our implementation of H.265. So as Aditya mentioned, about 65% of our users use Google Chrome, 28% use Microsoft Edge, 2.7% use Firefox, and then other includes mostly Safari. But I would like to see by raise of hand in here. Raise your hand if you primarily use Google Chrome. Let's see if this holds. Okay. Raise your hand if you primarily use Microsoft Edge. I didn't plan this, but this is working out well. What about Microsoft Firefox? We've got a couple. Excellent. Thanks for being here.
Quick question.
Yes.
Safari, is it Chrome? Is it a Chromium browser?
Safari is not. Safari was implemented by Apple, and it's basically its own beast.
And it is beastly, and that's why I'm a Chrome user.
Yeah. I use Chrome even on my Mac.
Yep.
So.
Do you see, just wondering, do you see any battery differences if you use Safari on Verkada versus Chrome on Verkada?
Personally, I have not experienced any degradation at all. Part of it is, I'm using a MacBook and using an M3 processor, so I don't have any impacts on battery life. But it is true that there could be some implications using Chrome.
Yeah, that's more so on the browser and how efficient the browser itself is. So it will just be like you visit any website other than like going to command. It's just effectively like how efficiently the browser will handle that.
Appreciate the questions, by the way. All right, so I was also going to throw out one quick anecdote about Firefox. When I was in college, this is my, I think, sophomore year of college, someone showed me the Firefox browser, and it was the very first browser at the time that used tabs. So if you can imagine what it would be like to use a browser that doesn't support tabs, I know all of them support it now, but Firefox was the big innovator with tabs, and it was life-changing to be able to use tabs. So I was a Firefox user for a while as well. Okay, so why is it important which browsers you use? So this is a matrix of which browsers support H.265. So all of the major browsers, Chrome, Edge, Safari, and Firefox. Firefox today does not support H.265. So if you're using Firefox as your browser and your camera is producing H.265 video, you're going to have that video transcoded to be able to play it in your browser. Now you see Safari has very good support for H.265, especially for versions after, everything after version 13. Edge, you can see, has decent support. Edge is a Chromium browser. And then Chrome announced support for H.265 in September of 2022. I remember that date very, very well because that was the exact date that we decided to implement H.265 across command. We wanted to be the first. We wanted to get that amazing video quality into your hands. Now, you might see there's shades of green on this matrix, and the reason is because, yes, the browser needs to support the codec, but also the hardware needs to be able to support the codec. So we did a little experiment on all of your browsers. I hope you don't mind. We embed a 1x1 pixel H.265 video in command. So every time you loaded command, this was 2 years ago, every time you load command, we would try to play that 1 pixel by 1 pixel video and to see if your browser and your computer was able to play 265. We found that about 73% of the computers and the browsers were able to play H.265, which was pretty encouraging and at the same time pretty discouraging. We're trying to figure out how we're going to be able to implement H.265 for your browsers without needing to transcode, because effectively what transcoding means is taking the video from one codec to another codec, so from H.265 to 264. And if we needed to transcode the video in real time while you're trying to watch it, it's a degraded experience. It's not quite as streamlined. So we wanted to try to minimize this experience for you as much as possible. I did add a quick pro tip here at the bottom. It is possible that your browser supports 265 and your hardware supports H.265, but if you have the setting in your browser to not allow hardware acceleration, then your browser thinks that the hardware does not support it, and you will have the transcoded or H.264 experience. So pro tip, by default, hardware acceleration should be enabled, but if it is disabled, that could lead to a worse performance. So how did we make it to where we could deliver H.265 as much as possible and reduce the amount of transcoding that you need to do? Without going into too much technical details here, our cameras can stream multiple video streams at a time, encode multiple streams. So we've got 4 encoders on the browser, on the camera. One of them is for high quality H.265 video, one of them for standard quality 265 video, one of them for standard quality 264 video, and then we also have another one called tiny resolution, which is primarily used for grids. But the innovation that we did here, one of the things that we implemented is this third encoder, the SQ H.264 encoder. So now if your browser does not support H.265, we will simply serve the video from the H.264 encoder, which means you don't have to transcode. I created this flow diagram. You don't need to understand it in too much detail, but the highlight is if your browser supports 265, great news, you get 265. If it doesn't support 265, we check to see if there's an H.264 encoder that's available to stream from, and we'll serve that. And if not, then you get the transcoded experience, which with this flow diagram is only about 2% of all of the video streams streamed through command. So we're able to maximize the H.265 video and minimize the amount of transcoding needed. Any questions at this point? All right.
We have a question.
Oh, great.
Okay.
Yeah.
How long do you guys plan to support H.264?
To be honest, I don't imagine us ever not supporting it as long as we've got browsers that might not support it. So one thing I've learned is that despite my best efforts, there are still people using Windows Millennium and Microsoft Internet Explorer. So we need to try to deliver the best experience to all of our users.
Thank you, by the way. It's very nice of you.
You betcha. We are always trying to obsess over every single frame. Every single frame counts. Yeah.
So does the command instant when launched monitor these things for you and give you that feedback? Is that how you know?
Yeah, so the browser has different APIs that our code can call in the browser to see what technologies are supported, and then we deliver the best technology that the browser
You have
supports.
statistics that you gather that, like every time command launches,
Yep.
what browser and what features and what's going on.
Yep, exactly.
So how do you bring that to the end?
I really ask, we have a large house population where our cameras are, and we keep on breaking everything. So what happens, we have the iCloud, we have the cloud backup. So, but how is your breakup? Because sometimes you don't catch the person like taking the camera off, or whatever they're doing to our core cameras outside. So what are you doing for, you do full like, for 5 minutes you're doing it and then you're offloading it? Or
I see, okay.
Minutes, or what are you doing on that?
Maybe I'll come back to this question at the end, simply because I want to make sure we get through the rest of the content. It's a great question, and I'm happy to answer it. Okay, so let's talk a little bit about time to first frame. So before we jump into time to first frame, I think it's helpful to understand at a high level how the internet, how the World Wide Web works. So before we do that, I just want to highlight that we migrated from HTTP1 to HTTP2 to achieve 50% lower time to first frame. How we did that? Now, cue up HTTP2. So in 1989, the images are loading slowly. In 1989, Tim Berners-Lee created a very, very simple one-line protocol called HTTP 0.9. This protocol was built on top of the TCP protocol. So basically, it would rely on two computers establishing a TCP connection between them. One of the computers would send an HTTP request across to the other computer, which is basically saying, hey, give me an HTML file. That's all it did at the time. It would request HTML files, and then the server would send that HTML file back to the client, and then the client can display the web page. And this was how the World Wide Web was first invented. So that was 1989. Fast forward to 1997. Over those intervening 8 years, different browsers and different internet companies were coming out. You might remember Netscape. And they would all implement their version of HTTP so that they could transfer HTML files across the internet and get HTML files. In 1997, people emphasized protocol, which is HTTP 1.1. Over those 8 years, we learned how people use the internet and what sorts of technologies we would need to be able to support with this new protocol. 2015, HTTP2 was first published, which is the next generation of HTTP protocol. You know, a lot changed from 1997 to 2015. Think about social media, think about video, think about Netflix. And so naturally the protocol needed to change to support new use cases. So you can imagine loading a web page, and imagine the purple box is your TV monitor. First, there's going to be requests to fetch all of the primary code of the web page. Index.html, the JavaScript, the CSS files. Next, you might need to load the ads. Naturally, they get prioritized to the top, right? Next, you might load your user information. So there's a request to fetch the user information. You have a news feed that's on the page. So you need to fetch all of the information for the news feed. That news feed has users in it, so you need to fetch the information about each of those users in your news feed. And then, of course, like you've got your notification panel up in the top right, and you need to get all of the data for your notifications. As you can see, there are a lot of HTTP requests that happen, and each one of these basically happens serially to the servers. And it's kind of a miracle to me that this even works, because if this was my dial-up internet connection trying to load this web page, it just would simply not happen. Now, with this is a screenshot from command. I tried to load command. You see in the bottom left, 485 requests just to load the initial experience. While you're viewing command, dozens and dozens of requests are being made continuously. So it's amazing the amount of data and the amount of requests that are being made. Now, why is that important? Because as I mentioned, this HTTP protocol happens on top of TCP. So for every single HTTP request from your computer to a server, you also need to establish a TCP connection, which is a 3-step process where between the two servers, you have an ACK, and then the server responds with a SYN-ACK, and then your browser responds with an ACK. So now you've established a TCP connection, and you can actually start the HTTP protocol. And if you imagine doing this before each and every one of those 485 requests, HTTP1 was fairly inefficient for this exact reason. Come along HTTP2, and they've simplified the protocol in a way where it establishes a single TCP connection. That connection is long-lived, and then you can make multiple HTTP2 requests across that same TCP connection, which is dramatically more efficient. So using HTTP2, we've been able to deliver a much better experience within command, especially on the video streaming side. Before, we had about a typical use case was 2.3 seconds to start one video, and today it is now 1.1 second. So hopefully you've noticed over the past couple of weeks, and as we continue to roll out this feature, you'll have much shorter spinning circles, and we can deliver that video to you even faster. I'll now hand it back over to Aditya to talk a little bit more about latency.
Thank you, Alan. So, looks like our image is not loading. Let's go back. All right, perfect. So Alan just walked us through how we were able to improve the video quality with H.265 and lower DTFF with HTTP2. Now let's talk about latency. To understand latency, you also have to understand playback. Playback is the process of playing media contents on your devices once it's delivered. Earlier in the session, I spoke about the importance of latency. By implementing a cutting-edge playback technology, we were able to reduce the latency, typical latency, by 65%. That has been incredibly impactful for a lot of our customers. And we did that by implementing web codecs. Web codecs provides an API that allows for more flexible and fine-grained control over the media codec. Before we dive into a lot of details, let's first understand what does a video playback pipeline actually involves. Well, it consists of 4 stages. The first is demuxing, then decoding, buffering, and then finally playing the media content. So demuxing or demultiplexing is the process that takes a single stream of data with multiple signals. In our case, it's usually audio and video, and it separates out those signals. So these signals were originally combined through a process called multiplexing, and demuxing essentially reverses that. It is separating out those signals. And earlier in the session, Alan spoke about the need for compressing of video using a codec like H.265. Well, decoding is essentially other half of that equation. It takes a compressed video, processes it, and spits out a full resolution streamable video. And finally, we have buffering, something I'm pretty sure every one of us has experienced in our lives. Buffering is the process of preloading media content before it can be played. Now, you must be wondering, what did we have before web codecs? Well, before web codecs, we relied essentially on media source extension, or MSE for short. Think of MSE like an old cassette player, where you feed in the media, which is the cassette, into this player, and it's a black box that provides you a set of actions of the buttons that you see, like play, pause, and fast forward. MSE, while it's a tried and true technology, and it's useful in a lot of different cases, it did not really give us a lot of control over how it handled media, or what was going on behind the scenes. All we could do is just play around with those buttons that you see. So, as over the years with MSE, we tried to optimize every single stage of the playback pipeline. And we realized the biggest opportunity for us to reduce latency is actually during the buffering stage. Unfortunately, MSE being a black box, we had no control over what and how it handles the media. That is a big motivation for us why we decided to actually move to web codecs from MSE. So if you actually look at the main difference of implementation, with MSE, we were restricted. We were essentially forced to make sure that we preload 12 frames or at least wait 500 milliseconds before any media could be played. But with web codecs, we implemented a playback experience that could process every single frame as it becomes available. That allowed us to shave off 400 to 500 milliseconds in latency, and was a major improvement in performance. Web codecs also gave us the flexibility of adjusting the buffer size based on the user's experience. So think about adjusting to bandwidth fluctuations. That helped us ensure that we deliver the best video quality and streaming experience in every possible case. Now with web codecs, we were able to reduce the typical live streaming latency from 2.6 seconds to 900 milliseconds. And in some of the best cases, if you have an amazing internet, we've even seen latency down to 500 milliseconds, which has been incredible. Now, just to sum up everything that we spoke about in this session, we spoke about how we were able to improve the video quality with H.265, reduce latency, reduce time to first frame with HTTP2, and lower the latency with web codecs. Well, our work didn't stop there. Our team has been working over the last few quarters behind the scenes to roll out a lot more features that have contributed to improvement in the customer experience. For example, variable bitrate. We spoke a little bit about earlier how we're able to optimize where and when the bits needs to be allocated. Tiny res, Alan mentioned that a little bit earlier, to ensure that we're optimizing the bandwidth consumption. And finally, media source for iOS to improve the experience for anybody who's using command on their iPhones. And the best part about all of this is that there is no need to upgrade your camera hardware. These features are delivered automatically. We upgrade them. We're rolling out HTTP2 and web codecs as of right now. So we're very, very excited for you to try out these latest improvements. Thank you. And then we're happy to take any questions anybody has.
Yeah, and I can even jump into your question first, and then we'll move on to more questions. I'll keep it somewhat high level, and if you want me to go deeper, I can go deeper. But super high level, video, as I mentioned, is recorded at 24 frames per second. There's this concept within video compression called group of pictures, which is basically how many different frames you have between your iframes or your reference frames. So with 24 frames per second and a group of picture size of 96 frames, means that we have a reference frame for every 95, they're called P frames, or the difference frames, okay? So we've got a 4-second GOP. So our video is saved on the SD card of the camera in 4-second chunks. Now, we also have to be thoughtful about how often we save video to the SD card. So we cache about 2 to 3 minutes of video in memory on the cameras. And then as soon as we get to 2 or 3 minutes of video, we then flush it to the SD card. Now, if we detect a tamper event on the camera, we immediately start flushing all of that video from memory onto the SD card, and we immediately start uploading the most recent video to the cloud. So, it can be as short as those 4-second segments that are uploaded to the cloud. Connectivity can affect it, and also, the speed with which the camera could be removed and the wire can be cut, for example. So we can only upload as much data as we can while that's happening. But does that answer your question?
Yeah, I was going to see how that
Yep. Okay, we got a few questions. Go.
To improve upon that, like how would you detect a tamper alert to if I'm cutting the wire? Like I'm not touching the camera.
Yeah. If they have access to the wire, there's really nothing we can do. As soon as that gets cut, the connectivity is gone, the power to the camera is gone.
And so in that case, there's always, with all of the Verkada cameras, you have free 30-day of cloud backup. So if the bandwidth is able to support it, we'd recommend you can always turn that on. So irrespective of tamper or not, it will still flush all of the video footage over to the cloud.
Also, I'll say that the video, the camera is recording right up until it loses power. So hopefully you still have some of the video once you get it back online. But okay, we'll go here.
So still, it's a great topic. Double clicking into that, you mentioned during a tamper event, is it the tamper event that gets configured low, medium, high, or does it have its own tampering threshold before it writes that 2 minutes?
So when you're configuring tamper alert, there is a default sensitivity, but there is a configuration and command where you can switch up the.
Right, but that's for events and alerts.
Yeah.
But what we're talking about is you writing your 2 minutes of cache to the SD card. Does that use the default version or the one that we selected?
Yeah, great question. I actually don't want to lie, so I want to verify, but I do believe it's the default, and it has nothing to do with your setting. I think your setting is specifically for the alerts, but I do want to double check on that.
Fascinating topic, thank you.
Yeah, thank you.
Do we have to put all the cameras on 265, or is it 265 by default? I know there's a setting in the
So we made it the default for all cameras. So if you get a new camera, it will automatically default to 265. There was even a point when we launched this about a year ago that we evaluated the usage and all of the customers' computers to make sure they can support it. And at that point, we enabled it across the board for everybody. Over time, I know there have been like very, very few instances of people that have switched back to 264, but by default, they should all be 265.
Yeah. So we have a question.
In the event that the camera is damaged, the SD card, is that something that proprietary is like that, or can we just get that data?
So the question is, in the event that the camera does get physically damaged and it's unable to work again, you know, what can be done? I hesitate to commit to doing this, but we have had customers that have sent those cameras back to us and we're able to get the SD card out. All of that video is encrypted, and the only way to decrypt it is with the data that we have on our server. So while you could take out the SD card and transfer the data onto a laptop, you would not be able to really use any of that data without decrypting it.
You have a question?
Yeah, one of our problems with the Verkada cameras is that they record 24/7, but they don't record high quality unless there's motion. So we'll have motion that's just a little bit further out. Camera doesn't detect the motion, does a recording, you can't go back to the recording and get quality view. Is there anything you can do with your compression that can enable high quality recording all the time?
I think that's a great feedback. So the question was around Verkada cameras always record SQ, but HQ is only recorded when there is motion. So when the camera is not seeing motion or somebody is really far away and is not able to detect motion, it doesn't record the HQ.
Sometimes it will detect motion far away, but then some motion it won't detect. So that we lose that quality when we're trying to go back and look at the incident.
Yeah. So to your point of one of the reasons that we always ensure SQ is because SQ records a specific bit rate, so we know exactly how much video that can be guaranteed based on whichever camera models that you buy, and that's a great way for customers to say like, hey, I want 30-day camera, 60-day camera. While HQ, it is a little bit more expensive in terms of storage and takes up quite a lot of space. So, and usually when there is no motion, most people don't really care if nothing is changing within the scene. And so what we wanted to optimize for was to ensure that HQ is always recorded whenever you see motion. Now there are cases that, as you mentioned, that some motions might be missed depending upon, the lighting, the placement of the camera, how far the person is. That's definitely great feedback. Right now we have no ways of extending HQ for 24/7. But that's definitely something we can
There's some
look
kind
at.
of compression you can use to do that.
So I do want to address something else as well. So number one is that we're given the walk-off music here, by the way, so we'll have to wrap up here. So two things that happen here. Number one is with the HQ video. As Aditya said, we store the guaranteed retention of SQ video. And then for the HQ video, we store as much as we can with the remaining storage on the camera. So you can do a couple things. Now, one of the instances that you're talking about could be related to the fact that, by the time you go and watch that video, it's so far in the past that we no longer have that HQ video and we only have the SQ video. In those cases, one setting that we do have is you can adjust how much retention of SQ video that you have. So you might have a 30-day guaranteed camera. You can shrink that down to say 15 days, and then that remainder of storage can be used for the HQ video. And so you will then have a longer period of HQ video, and that might solve some of your use cases. For the other use cases that Aditya mentioned, like from a technological perspective, the thing that is really challenging is figuring out how to guarantee storage. So, potentially in some hypothetical future, we say you can enable HQ video 24/7, and you will be able to store as much video as possible, but we can't guarantee how much video at that time.
We are given the walk-up sign, but we'll come down the stage, so if you have any questions, please feel free to come to us and we'll happy to answer those as well.
Thank you all,
Thank you.
appreciate it.